Welcome back to the Deep Dive. Today, we are taking a fascinating plunge into the world of computer use agents, or CUAs. These are the ambitious AI systems designed to operate complex software for you. And we're looking at research that tackles what might be the single biggest roadblock keeping these agents in the lab and off your desktop.
And that roadblock, well, it really defines the whole mission of this deep dive. A vision is so powerful, AI that can automate your workflow across any software. But the execution just keeps hitting a wall.
And that wall has a name.
It does. The core problem, the one we're really focusing on today, is called grounding.
Okay, so let's unpack that. Grounding. For an agent to work, it has to take a high-level instruction from a user and then turn that into a very specific action on the screen.
Right. Grounding is that final, absolutely crucial translation step. It's connecting a natural language instruction like click the export button to the exact pixel coordinates of that button.
And if it's off by even a little bit?
The whole task fails.
Yeah.
Instantly. It's a game of millimeters in a world of, well, millions of pixels.
This is where it gets really interesting, because the complexity just explodes when we move to desktop environments. Why is grounding on, say, a professional design application so much harder than on a simple website or a mobile app?
Well, desktop UIs have their own unique set of hurdles. The first one is just the sheer scale.
The resolution.
The resolution. We're talking about high-res displays that can range from 0.4 million all the way up to 7 million pixels in the data they studied. A web page might be like reading a letter, but a professional desktop application, that's like trying to navigate a sprawling, dense engineering blueprint.
So it's a needle in a haystack problem, but the haystack is enormous.
A huge haystack.
Yeah.
And it's full of things that look like needles. Desktop apps often have these really dense layouts, visually similar elements everywhere. Think about a ribbon bar with like 20 tiny gray icons that all look kind of the same.
And it's not a static blueprint either, right? It changes based on what you're actually working on.
That's the other layer. High variability. The user screen is full of dynamic user-specific things. Custom spreadsheets, blocks of code, unique documents that the agent has never seen in training. It has to operate in a genuine, messy context.
I can just picture an agent trying to follow an instruction like open the color picker in an app like FreeCAD. It has to pick out one tiny palette icon from a dozen other lookalike tools right beside it.
And previous attempts to train agents for that have struggled. They often relied on noisy data from accessibility signals or very simple synthetic inputs.
Which is what led to this new work, the creation of GroundCUA.
The researchers saw that for agents to work reliably on these complex apps, they needed deep, expert-driven supervision, not just throwing bigger and bigger volumes of low-quality data at the problem.
So let's get into this data set, GroundCUA, because it seems to set a whole new standard. How did they make sure the data was actually representative of how people use these complex tools?
The foundation of it is expert human demonstration. The process was painstaking. They had trained annotators design and then execute over 10,000 real-world tasks.
10,000?
10,000 tasks across 87 different open-source applications. And these apps covered 12 categories, everything from productivity tools to scientific and graphic software. So you get a really realistic distribution of complexity.
And that focus on expert use is so critical. What are the numbers that really show the density and quality of this data?
The overall scale is big, 56,000 screenshots, over 3.5 million human-verified annotations. But the density is the number that really matters. Each screenshot has an average of 64 distinct annotations.
64 on a single screen?
On average, yeah. That's more than 3 times the density of other comparable desktop datasets. Some of their images have up to 542 annotated elements on one screen.
Wow. That's an incredible amount of human effort to verify every single interactive element. It tells you they weren't just scraping this. And what about the size of those elements? What does that tell us?
It shows they were focused on the hardest part of the problem. The average bounding box for an annotated element covers only 0.13% of the image area.
So tiny targets.
Tiny targets. It confirms they were specifically capturing and labeling those fine-grained challenges, the small icons, the little controls, the menu items that automated systems just miss.
And with that kind of dense, high-resolution labeling, they could then generate much richer instruction sets for training the agents.
Yes, and understanding the 3 types of instructions they created really shows you how versatile the training was. The first type is what they call direct instructions.
Okay, so that's something like click the blue button with the text save on it.
Pretty much. It's explicit. It refers directly to the element's attributes or its position.
Yeah.
Very clear.
And the second type?
The second is functional instructions. These are more about the goal. So you don't say, click the tiny gear icon labeled settings.
Mm.
You just say, open settings.
Mm.
The agent has to figure out the visual connection itself.
That feels much more robust, much more like how a person would actually ask for something. What's the third type?
The third is spatial instructions. These use relative positioning, something like click the icon to the left of the file's menu. By combining all three, they build a really comprehensive foundation for a context-aware agent.
The quality of the data is clear. So the natural next question is, how did this level of detail translate when they actually used it to train a new generation of models?
So they built the GroundNext series. These are vision language models, built on the Qwen 2.5 architecture at both 3 billion and 7 billion parameter scales. And the training was a two-stage process.
Stage 1 being the main learning phase.
That's right. Stage 1 was supervised fine-tuning, or SFT. They trained the models on 700,000 curated image instruction pairs from GroundCUA.
And stage 2 sounds more like a refinement step.
It was. Reinforcement learning, or RL, post-training. They used a smaller set of 10,000 elements the model had never seen before. They used a specific method called RLOO to help the model learn to tell the difference between very similar-looking elements, along with a pretty basic reward function.
And this brings us to what I think is the most critical finding in the paper: data efficiency. What did the high quality of this GroundCUA data let them achieve?
This is a huge insight for the field. GroundNext got state-of-the-art results using dramatically less training data than the models that came before it.
How much less?
A lot less. Take JDI, a previous top model. It needed 9 million data points. GroundNext needed less than a tenth of that, just the 700,000 samples, to build an incredibly strong baseline.
That is a staggering difference. If that first SFT stage was so effective on its own, why bother with the second RL stage? Was that extra complexity worth it?
That's a great question. And the answer is, sort of. The quality of the data let the SFT stage do most of the heavy lifting. The SFT-only models already had the highest average performance across the board. The RL stage did give a small, consistent boost, but it was a modest one.
So the better the initial training data, the less room there is for improvement from reinforcement learning.
In a way, yes. The high-quality supervision was so informative that the model made fewer errors to begin with, leaving less for the RL stage to correct. It really supports the idea that investing in good supervision is better than just getting more data.
All right, let's talk about practical utility. How did this data efficiency translate when the agent had to perform a sequence of actions where one mistake ruins a whole task?
For evaluation, the metric is simple. A prediction is correct if the agent's predicted click point lands inside the correct bounding box. They tested this on the OSWorld verified benchmark, which simulates these real multi-step tasks using an existing planner system.
And how did their smaller, more efficient model do, the GroundNext T3B?
Its performance really shows how effective the training was. The 3 billion parameter model achieved an overall score of 50.6. Now that's almost identical to the 51.0 score from the much, much larger GDI-7B model.
So you get comparable performance from a model that's less than half the size.
And it blew other open source models in its class out of the water. One comparable model only scored 17.7. This really shows that high-quality grounding data solves a major efficiency bottleneck.
And I'm guessing the performance gains were biggest in the areas where the dataset was most detailed?
That's absolutely right. The largest performance boosts were on the key desktop benchmarks. And crucially, the model showed superior icon recognition. It outperformed most other models by an average of about 10.7% on the benchmark that specifically tests that, which goes right back to the dataset's dense annotation of those tiny, common desktop elements.
What's really fascinating, though, is that even though the training data was all from desktop apps, the skills seem to generalize.
Yeah, that was a surprising strength. The larger 7 billion parameter model, after RL, performed competitively on mobile and web benchmarks too. This suggests that learning to handle complexity in one domain gives you transferable skills, probably because a lot of UI patterns are shared across different platforms.
So if we step back and look at the main takeaway here, it feels like a really powerful message for anyone trying to build these kinds of reliable AI agents.
It is. The research makes a very compelling case that high-quality, densely grounded supervision from expert human demonstrations. It's just a much more effective driver for performance than sheer data volume. It suggests that focusing your resources on getting that informative ground truth pays off in ways that massive scale alone can't match.
And as this work sets a new benchmark, the researchers also pointed to the next frontiers. Where does this research go from here?
They identified 3 main challenges ahead. First is dealing with dynamic UI elements. things like animations or real-time data updates, which a static screenshot is going to miss.
Things that move.
Things that move. Second, they suggest systematically studying more complex reward designs for that RL stage, moving beyond the simple one they used here.
And the final one seems to be about continuous learning.
Yes. They really stress the need to explore how these agents can continuously learn and adapt to totally new applications they've never seen before. I think the ultimate goal is still an agent that can learn and adapt just as fast as the software world itself changes.